Okay, so today we're going to look at section 7.4, the nonlinear system of equations and inequalities. So what is the solution to a nonlinear system of equations? Well, it's the same concept as when we had the solution to a linear system. In this case, the solution is going to be where the graphs, the x-coordinates of the graphs intersect. So take all the graphs in my system where they all intersect in a single point or points is where we will have our solution. In a linear system, we had one solution, no solution, or infinite solutions. And here's what it looked like. If we had one solution, the lines intersected in one location. If we had no solutions, then the lines did not intersect. And if I had infinite solutions, then the lines were basically the same line. So they intersected in every point along the line. Well, in a nonlinear system, it's very much kind of the same. I can have no solution, which means there is no intersection between the curves. I can have infinite solutions. Okay, in an infinite solutions, two or more of them have the exact same curve or line. Or I can have from one to infinite solutions based on the number of times the graphs intersect. So I can have infinite solutions if I have the same curve, but also I can have infinite solutions if the graphs intersect an infinite number of times. Now, in our world here in this class, Algebra 1, we will not get graphs that intersect an infinite number of times, but do know that that can happen later on. Okay, so we're going to be looking at a graphical solution. I have an example we're going to look at here, but how am I going to do the graphical solution? Well, just like we did before. We're going to graph each curve. We're going to label it appropriately. We're going to try and draw this neatly as we can so that we can find the points of intersection if there is any. Remember, this is an approximation unless we actually check the solution. So once you think you have a solution, you plug it in. We can do this on a calculator for very complex equations that we maybe can't solve algebraically later on. So if I use a calculator, and we've done this before in class, and there is a video on intersecting points of graphs, make sure you round your solutions to 3 decimal places. Once we have our solutions, they are the x-coordinates of the intersecting points. So we write them as x equals values. So I have an example that I'm going to show you and walk you through. So here we go. In this example right here, my system is a quadratic, negative 5x squared plus 6x minus 3, and a line, negative 4x minus 3. And I'm going to graph those and see if I can figure out the points of intersection. Okay. So to do that, we graph each individual piece. So this is a quadratic. So to graph a quadratic, I want to find the vertex. So I'm going to be doing the negative b over 2a. B is 6. A is negative 5. And so taking this fraction right here and reducing it, I get a positive 3/5. So I'm going to make my table. My XY table for the quadratic. The vertex will be in the middle. It's going to be at 3/5. And then I want to find that vertex. Then I pick 2 numbers above and 2 numbers below. Since this is a fraction, it's the only fraction I want. The rest of them are going to be integers. So a number bigger than 3/5 is 1. And then the next one is 2. And then less than that would be 0 and negative 1. Now, I know a lot of times when we do this, you expect to see a very neat pattern in our numbers down here, but that's when everything is balanced. If you look at this, I want you to make a note. See how this is 3/5? It's not in the middle between 0 and 1. It's closer to the 1 than it is to the 0. So these answers are all going to be different. You're not going to see that neat pattern that you usually see for quadratics. That only happens when everything is evenly balanced between all the values. So saving some time, we can go into this thing and plug in these numbers and get these answers. I've done so already, so for the sake of time, this right here will yield 1.2. This is a negative 2, negative 11. At 0, we get negative 3. And at negative 1, we get negative 14. Okay? For the line, we do a table for the line, we only need 3 points. And usually it's right in the middle, so we'll do 0, 1, and -1. And we plug them in and we get our values there. So this will be -3, -7, and +1. And so we're going to graph both of these tables, drawing our curves in there. So I'll start with the quadratic. So our vertex is going to be at 3/5 and a -1.2. And 0.2 is 1/5, just so you know. So 3/5 is about right there. And a -1.2 is about right there. So that right there would be my vertex. At 1, we're at -2. At 0, we're at -3. At 2, we're at -11. And at -1, we're at -14. So it's a very skinny one. And so do the best that you can for these things. And we'll draw this one. So there's the parabola for that one as best as we can draw it. We'll come back and label at the end. So the next one is going to graph those dots. So 0, -3, so we got a point right there. 1 goes to -7. And -1 goes to +1, which is up there. So we'll take our straight edge and we'll draw that. Trying to be as accurate as we can. And what we notice here as I draw this thing, life was kind to us. We see that we have a point of intersection right here at 2, -11, and one right here, which is at 0, -3. So those are the 2 points on the line. Label the vertex here at 3/5, and a -1.2 for the vertex. And all the labeling is now done. But I see that the point of intersections are right here and right here, which means my solutions to this system is when x equals 0 or when x equals 2. So those are my solutions to this nonlinear system graphically. Okay, that's the graphical solution. So the next thing I want to do is, how do I solve something like this algebraically? How do I solve it algebraically? And for that, I'm going to use this paper right here. We're actually going to show the same solution here so you can see it done. So algebraically, so we're going to do y equals a -5x² plus 6x minus 3, and y equals -4x minus 3. Okay? So in solving something like this, remember when we talked about systems before, your main process for solving a system algebraically is to use the substitution method. So this one requires the substitution method. And if you remember, the substitution method is what we do is we take one of these equations, we solve for one of the variables. Well, luckily for us, they're both solved for y. They both say y equals. So taking one of them, if I put it in parentheses, if y equals that, then I can substitute this into the other equation for y. And so what I end up with is one equation with one variable in it. And that's the substitution method. Our goal now is to solve this quadratic equation. So to solve it, the first thing we have to do is get everything to one side. I always like the squared term to be positive, so I'm going to move these 3 terms to this side over here by adding the opposite of all of them. And then I'm going to line it up according to our like terms. So this 3 will add to 3 here, minus 6 to this, and then plus 5x squared. And when I add all these up, everything on this side becomes 0. And this side is 5x squared minus 10x plus 0, so I don't write anything, equals 0. So now I have that. Once I have it equal to 0, then I can use many different techniques to solve this. Looking at it very quickly, I can see that factoring technique would be the best choice here. And so I'm going to find the common factor here, which is 5x, and then factor that out, and I get x minus 2. Now I have a product of two factors equal to 0, which means 5x equals 0, or x minus 2 equals 0. Solve each of these individual ones for x, and x equals 0, or x equals 2, confirming our two solutions on our graph. X is 0 or 2, the points of intersection, and we have confirmed it algebraically over here. Substitution method. Okay, so that is equations. So we can do a graphical solution, just graphing the functions that are there. We can do an algebraic solution. Okay, so solving it this way using the substitution method. And so the last thing we want to talk about in here is a system of linear inequalities. So nonlinear inequalities. So we just, in the previous section, did linear inequalities, and we realized that the solution to a system of linear inequalities was a overlapping solution region. Well, the same thing applies here. So we're going to graph everything. We're going to determine whether or not we have where our shading goes based off of a test point, just like as if it were a linear system, and we'll get a solution region. So how do I find it? We're going to graph each boundary curve or line, depending on what they are. Draw it as a dotted if I have these symbols, solid lines or curves if I have those symbols. Make sure you label each of your graphs appropriately for whatever is required of them. We're going to do a test point to determine the shading, and I'll show you how that works. Okay, and then we're going to kind of highlight our emphasize our solution region. So I have another example I want to look at on that one. So we're going to graph this one. So this is a nonlinear inequality system with an absolute value and a quadratic in it. So we need to make a table for each one of those things. And the top one right here will be a dotted curve, and this one right here will be a solid curve because of those symbols. And so let's do the top one. We'll make a table for the top one. It's an absolute value. So just like from the quadratic we're going to do, it's in the same kind of format. Where is the vertex for this thing? Remember, if you don't, absolute values are like this, right? X minus h plus k, so hk. So what makes that 0 is -3, so that is the middle of my table, -3. This number right here is k, so -5 is the y part. You pick two numbers above, two numbers below. You plug those in, and you find these values. So I've already done it, so I'm going to go ahead and show you what these are. This is -3, -4, -5, and then -4, -3. And if I need one more point, which I'm going to put in 0 here, okay? And then that's the y-intercept, and that gives me -2. And you can see the pattern here for the absolute value. Let's go ahead and take a look at the quadratic and make a table for the quadratic. The quadratic is in vertex form also, so it's very easy to pull out the vertex for this one. What makes that 0 is -1. 1. There's the vertex for the bottom one. Two numbers above, two numbers below. And we might go one more over here just to make sure. Plug these numbers into that and solve it out, then we get -3. This will be a 0, 1, 0, -3, and this is -8. And again, just to find those values, you just plug them into your equations and find the y values to go with it. So let's go ahead and graph this. We'll graph the absolute value first. Remember, it's going to be a dotted curve. So we put our dots in here. We're going to graph -3, -5. And then we have a dots at -2, -4, -1, -3, and here 0, -2, and then on this side, going up on that diagonal also. And so then I can use my straight edge and draw this. Now, again, just like before, be careful. You know it's a dotted line, so line everything up, and don't forget to draw it as a dotted line. You want it to be long. You don't know where this is going to overlap, so you want to make it long enough that you can make sure you cover all the possibilities that can occur. Okay? Don't make a little short graph because you may not be able to see the overlapping regions. And if you can't see the overlapping region, you'll have to redraw your graph. Okay? Arrows on the end. And we'll label last. We'll come back and label points afterwards. So there's the top boundary curve. I have not done shading yet. We'll do that after we graph the other one. So the other one we're going to graph right here, put in our dots. 1 goes to -3, 2 goes to -8, 0, 0, -1, 1, -2, 0, and then -3 is -3. And because of symmetry, we know that the next one is going to be over here at -8. So -4 is going to be -8. And I can go ahead and draw that in here too. So you should be able to see your parabola right there. So we're going to draw that in. Remember, this is a solid curve. Okay. And you can go ahead and let's determine our shading at this point. So I got 2 curves. Okay. So on this one, you can see that I have a region that is on that side, and then I have a region that is on this side. Okay. So we need to do a test point. So for the absolute value, I can pick any point I want. Okay. 0, 0 is here. I can pick it because it's not on the boundary curve for the absolute value. So for my test point, for the absolute value, I'm going to plug in 0, 0. And so is 0 greater than the absolute value of 0 plus 3 minus 5? Is 0 greater than 3 minus 5, which is -2? Is this true or false? And 0 is indeed greater than -2. So that means I will be shading on this side of the absolute value. And just like all things, you want to shade in one direction only. Don't scribble. Just do little line segments in one direction where the shading does occur. Don't draw it dark because you're going to be looking for the overlap and you don't want to lose the other graph in there. So now I have the parabola we're going to do. We need to find a test point. Notice this time I cannot choose 0, 0 because it is on the boundary line. So I can choose any other point I want. So just find another point somewhere. It doesn't matter which one you choose. Let's do another one. Let's do 1, 1. We're going to do this point right there. Okay. So if I do the test point 1, 1 into the parabola, is 1 less than or equal to a negative 1 plus 1 squared plus 1? Is 1 less than or equal to, this is going to be a 2 squared, okay? And then that makes it negative. So this is going to be a -4 plus 1 or -3. Is 1 less than -3? And the answer to that is no, it's not. So this point then would not be on my solution. okay? Which means since this point is on this side of the parabola, then the solution region is on the inside of the parabola, and so shaded in a different direction than we shaded before. So this is the solution region for the parabola, and we can see right here, this is where it overlaps. And so you want to, darken that a little bit, make it stand out, emphasize it in some fashion. You can do a highlighter. You can use, like I said last time, we can do a little rubbing like that to make it stand out. Now, we're not done yet, because what I haven't done yet is I haven't labeled things. Always label your curves. And then this one down here is y is less than or equal to negative x plus 1 squared plus 1. Label your key points. So the vertex here, negative 1, 1. The vertex here was negative 3, negative 5. Pick a point on each side. So this point right here is 2, 0. And you pick any number over here. So we got negative 5, negative 3. And then we want to pick some points on our parabola, 0, 0, and then one on this side, negative 2, 0. And so I have 3 points on the parabola, 3 points on the absolute value. Okay. If I knew those values, then I can use them for both, but I didn't know them. And I don't want to figure them out. And so this is what I'm looking for. This is your solution to this nonlinear inequality system. Okay. And that's how you would go about doing it. We'll do more together in class. That ends this video.